You're
The
welcome.
next presenter is Dave Risk. He's professor of Earth Sciences at St. FX in Antigonish, and he holds the GeoVera Chair in Emissions Research. His Flux Lab team consists of almost 20 students and researchers, all working on projects related to greenhouse gas and methane measurement. Dr. Risk.
Thank you, and you can hear me okay?
Yes, thank you.
Okay, great. Yeah, it's a treat to be able to talk about the lab and our work. So thanks very much, Larry, and I've really enjoyed seeing all the other presentations as well. So I'm resident at St. Francis Xavier University, and it's a university, primarily undergraduate university in Nova Scotia. We're on the eastern mainland, out near Cape Breton. We have about 4,000 students here. And fun fact is that we're one of the only face-to-face universities right now in COVID-free Nova Scotia. So things are pretty much business as usual, which is really great. So at the Flux Lab, which is my research lab, is focused predominantly on greenhouse and other gas measurements. So my interests are really in using gases as diagnostic indicators of processes, whether natural or industrial, and also in developing and helping others develop better measurement and instruments. So we have a footprint because we also work in some natural systems too. I mean, 80% of our work would be in oil and gas, or in carbon capture and storage or CO2 injection, but we do also have research activities ongoing from the Antarctic to the Arctic, and so that was sort of originally my research area, and my portal into oil and gas was through carbon capture and storage, CO2 injection, looking for CO2 fugitives coming from sort of around the wellbore system, gas migration type projects, or elsewhere in designing monitoring programs. So I've been involved in Aquastor, Quest, and Wayburn and other similar projects for detection and quantification and fingerprinting. And so that work goes back about 15 years now. And the methane work that we've been doing has been around for about 7 years when methane started to really become the gas of interest. So this is an old picture of our research team. So we don't have a recent picture because we haven't been in the same room for a little while, but we're about an even split between engineers and environmental scientists and data scientists. So we've traditionally maintained a larger population of females than is probably normal, I think, in STEM-related grad studies, and so that's been great. And then, as I said, all our work is related to gases. So I have the talk organized in a few themes. First, I'll talk about technology development and testing. So we're developers. Originally, we were developers of soil gas instrumentation to measure flux rates of carbon dioxide or methane or other gases, and also isotopic techniques. We have several patents in those areas, and those patents resulted in a spin-off company more than a decade ago called EOSense, which has been happily percolating away since then. And a lot of that technology development and testing is informed with numerical modeling as well. Other than soil gas instrumentation, we've done work with fiber optic sensors with Peter Wild and others at UVic. And those fiber optic sensors were gas sensors that could be used in the aqueous and high pressure environments where we couldn't power sensors. So we were operating that project both for subsea monitoring of either pipelines or wellheads. So we did that for the Deep Chinook project offshore Nova Scotia here, and also for carbon capture and storage, and a lot of that work was through Carbon Management Canada, which was, as many of you know, a University of Calgary aligned project. We've also had many commissions over time to develop instrumentation. So we had about, for example, 10 continuous soil gas monitoring stations that we built for NASA, a NASA program in the Arctic that were going for many years. And in total, we probably had maybe had 20 of those polar greenhouse gas monitoring stations operating over time that we've built here. We're very good at building cold regions equipment. That's also very low power as well. And so I also have pictured here a drone sensor that we built for oil field applications that saw a lot of use last year. And I have also pictured a stationary methane monitor, which is a tripod there. That's something else that we've been working on with an industry partner. And you can see in one of the bottom images, there's the back of an ATV here. We've done quite a lot of mobile methane measurement work and trying to refine techniques for collecting those data while moving and especially processing it, because that's a bigger challenge. So in the lab, we have to support the technology development and testing projects. We have our own machine shop, first of all, and there's also a machinist on staff right now on the university staff right next door with even more equipment. We have controlled release equipment. We have 3 different controlled release setups that we've used over the years. And we have an environmental chamber and blender system that are coupled to one another. So we can take new sensors and put them in the environmental chamber for stress testing and expose them at the same time to different gas concentrations for either calibration or stress testing. We have many Picaro analyzers and LGR analyzers for bulk concentration analysis or isotopic analysis. And we frequently help others as well. So several of you would have Picaro analyzers. When Picaro is developing analyzers, they'll often send beta versions here for initial testing and stress testing because we do have a good setup for supporting those kind of activities. National Research Council as well. We're working with folks there on methane sensor development too. Okay, and so this is an image of the lab and just some of the benchmarking equipment or one of the labs at any rate. And you can see all the gas cylinders, and with our blender system, we can weave those into different concentrations on automated programs. So we're also field scientists. We undertake studies of fugitive and vented emissions, and there are several thematic areas that I'll identify. So one is soil gas migration, and pictured from the back of the truck, there's a lead that's extending to a measurement head that sits on top of the ground. And so this is a special measurement that we're able to make using a Picaro and analyzer in the back of the truck, and we're able to make a compositional flux measurement. So in about 5 minutes, and so we can do this around different areas of a well site or close to well bores to try to establish well bore, whether the well bore system has good integrity or whether it's losing gases into the soil. So we can quantify the rate at which those gases are being lost, and we can also identify coarsely anyways which of the what contribution is from a thermogenic source. And we would rely on Scott Mundell or others afterwards to do more fingerprinting work. But this is the type of analysis that we see as more likely the future from some of the current gas migration testing, just because it's much more diagnostic. It provides more useful information without adding extra time, particularly. We also do fugitive and vented emission studies using trucks. So this image does dual duty here, because you can see the anemometer mast on top of the truck. So this is the same truck that we would use to circulate through oil and gas fields and to transect across plumes and to measure the intensity of emissions from various sources. So this is the algorithms to do this we've commercialized, and GeoVera has those and offers them commercially. It used to be Altus, Altus Geomatics, but Altus recently merged with WSP, and the new company is called GeoVera, and so they do all the commercial work. We still do some from the lab, however, where I'd say there's a strong research component that's added. So it might be that there's additional FLIR camera work. We have a FLIR camera, or OTM measurements. For those of you who know what OTM measurements are, it's an EPA test method. Or if there's a gas migration component that goes along with the truck measurements, then we will do those sort of studies from the lab. And we frequently get requests from producers and from government to go out and measure, X number of facilities, and so we will do that. In fact, we just had a group that just came in from 6 weeks of field work. We have many papers out that shed light on geographic variation in venting and fugitive emissions through some of the Canadian oil and gas environments. We've also done exploration studies with the truck and with gas migration equipment for exploration companies. There was a question earlier on about whether any of this work could be used in that context, and sure, it's regular to do soil gas investigations ahead of drilling. It's one of the ways that we've always been able to identify oil and gas plays is through surface show, and also legacy well studies. We've done quite a number of legacy well studies, and we have a paper published on legacy wells in Atlanta, Canada. So the third thematic area is monitoring of CO2 injection. And so we're still active at Aquastore and with Whitecap at Weyburn, for example, in looking for CO2 fugitives. And methane's an important part of those studies as well, because it's one of the indicator gases alongside carbon dioxide of any problems. And we've not ever seen any problems at any of the Canadian sites, but we're at those sites fairly routinely, and we also use radioisotopes there too. And then we have sort of the other projects. We've done, for example, H2S studies in Saskatchewan with SRC. The drone that you see pictured here is a long-range drone. We've been working with ISS Aerospace, and that hydrogen fuel cell drone, we're able to fly it for a couple hours at a time outside of field of view in these projects. And so we can do monitoring of gas concentrations over 150 kilometer route, which is obviously very efficient sort of monitoring data. So anyways, it's this lab and field experience that we bring to our CanERIC projects. But also we do quite a bit of data computing, and we have some footprint in economics work. We've been involved, for example, in PTAC projects to aggregate methane data from the Canadian oil and gas industry, and built a big repository of anonymized measurements that anyways, again, are very useful in specific contexts for those who need those type of data. We do satellite projects as well, data analysis, algorithm development for methane, but also for processing land use data. And our work in the data space resulted in the formation of another company called Aerolytics, and some might be familiar with Aerolytics. And we've been involved in a new project with Aerolytics. Aerolytics has a cost model for alt-FEMP projects. And so for those of you who don't know what alt-FEMPs are, industry has to measure methane, and a fugitive emission management program involves methane measurement and then management or mitigation. And the alt part stands for alternative. It's where we would use alternative detection strategies, alternative to what's prescribed in the regulation, because other possibilities are available. The regulator opens up the possibility for using other techniques, but one has to prove that they will reduce methane to the equivalent level, and they want them to be cost effective. So alt-FEMP programs should result in lower costs for most producers. And so we have a project right now that is trying to look at where we're modeling opportunities across the sector for different types of producers in different regions. And I think that that's important work because it helps point at low-cost solutions for producers. And so you'll see results from that soon. And then, yeah, that work especially comes out of former work done in carbon capture and storage, where we realized the cost is really important in any sort of monitoring or mitigation project. So for our CanERIC roles, there are 3 of them. So the first is that is to provide air-like benchmarking gases to those who need them. So the testing network needs to have some ability to standardize where methane measurement is occurring. So other networks that I'm part of do. So we'll compress high pressure cylinders with benchmarking air in air-like, as I said, in air-like concentrations that similar to what we've seen in oil fields, and provide those free of charge across the CanERIC network to those who need them. We'll have cylinders here, and we'll be able to run a swap program. We also have a metrics contribution. There's a lot of great work going on in CanERIC, a lot of great studies, but also elsewhere as well, like METEC in the US. And so we want to aggregate sort of reports around tested technologies and bring them together and be able to communicate them within the CanERIC network for our producer partners. And then we also want to track the services sector that's being built up in Canada sort of around methane and mitigation, because it's an important area of economic stimulus that we're providing, and so some of the government partners are also interested in that too. And producers as well, they might want to know who's up and coming and what's up and coming. So we have a metrics project, and then abatement data studies are something that we'll continue to do, where we will combine information on what works with the costs of what work, and try to measure or try to model cost curves for producers working in different regions who have somewhat different challenges. Okay, so please contact us if you're interested in gas cylinders, for example. We have no formal testing role right now in CanERIC. We're a little bit in the wrong geography for that, but at the same time, we do have these great bench testing facilities, and so we could do in-lab projects, or we could also loan field type equipment as well to people. We're willing to do that. So we have a great website. Please visit. And we also have good social media channels that you can drop in. There's some good news and blogs on the website, and videos there as well. And much of our social media presence is aimed at attracting students to the group, but it's useful for everyone else as well. So that's our story, and I look forward to contributing to the CanERIC mission. Thanks.
Okay, open up the floor to questions for Dave. Thank you, Dave. Okay, I have a question. I remember hearing one time about CO2 storage on the ocean floor, where you just inject CO2 as a dense fluid. Is there any more discussions about that, or is that something that was, well, if that ever let go, it would all be in the air instantly?
Yeah, I'm not aware that there have really been any test projects or anybody seriously considering that. We do have so many good geologic opportunities, especially in depleted oil and gas fields, and so I think that those would be everybody's first choice. And there are obviously some that are not too deep underneath the seafloor that we already have pipe into. And so those would probably be our first opportunities, I think, and those are still opportunities that are being pursued. I'm not aware of any of any real ocean floor disposal like that, because it would be potentially unstable, as you say.
I have a quick question. It's Sean Forrester with Husky. I'm just wondering, we do kind of run into sites where they tend to be underwater, like say in a slough for basically the entire year, or that they actually freeze over during the winter months. Do you see any challenges with those type of situations?
You're talking about like a soil gas measurement context in particular?
Yeah, like adjacent to a wellbore.
Yeah, in the liquid environment, that's not really a problem. We have published papers even on continuous monitoring devices for floating deployments, and so that can be managed pretty easily. That is a big challenge for some of the current techniques, which generally involve some like needing airspace in the soil in order to sample gas migration, like the current sort of bar hole technique that most people use doesn't work well. We actually at Aquastore use waterproof soil vapor implants, and so they basically come to equilibrium with the gaseous environment. So that's one option. And then chambers on the floating chambers on the surface work. In the winter, it's more difficult, of course, because the ice will hold in the gases below, and it will come out through cracks and another strange conduits. So it's harder to understand where it would be coming up. So winter is a bit of a different challenge. If the soil is drier on the surface, winter isn't a big deal. But like a frozen aqueous environment is a little tougher. But if you want, we can chat offline about that. I mean, it's definitely something we've confronted in some of our Arctic projects, and a lot of that Arctic experience is probably quite useful in the industrial gas migration context. But I know that most of the Canadian regulations don't require any real winter monitoring, but there would be reasons that you'd want to.
For sure. Yeah.
Dave,
like,
if I could.
Oh, go ahead. Yeah, I'm done.
Sorry, Scott Munnell, University of Windsor. Depending on the puddle, often we've had success with just regrading the pad, and you still end up with a little bit of water underneath it, but it does give you a surface to work from with some porosity that these techniques would work well on. I mean, if the water's deep and it's a large area around the wellhead, it's a bit of a different story, but for sometimes regrading it allows you a means to be able to be a little bit more accessible with some of these techniques.
Yeah.
Excellent. Well, thank you very much, Dave.